Thank you for the chance to get up here and present a little more data. Carl mentioned the PARSync system. He described, I think, I may have blanked out, but I think he described how it uses 3 different methods for measuring particulate. And what I'm going to talk about is using that same system in a different way. The PARSync is actually targeted at the PEMS market. It's kind of the next generation of PEMS, research-oriented, kind of an open-ended use. And what I'm going to talk about is maybe adapting that system to a more specific use, namely inspection and maintenance, identifying normally emitting vehicles from failing excessively emitting vehicles. So, I get it right. First, I'll give you a little background on the inspection and maintenance programs, not in general, but specifically for the diesel market. Then I'll talk about how current diesel IM is conducted very briefly. And I'll talk about the PARSync and then what we've started to work on in making that system duty specifically for the IM market. And I'll describe that. And then we did a little blind test of that concept, and I'll describe those results. First, the background. Now that most diesel vehicles have after-treatment systems, the engine out emissions get reduced by a factor of 10 or more. So it's a highly leveraged situation where a properly operating after-treatment system will have very, very low emissions, but even if that system starts to deteriorate a little bit, the emissions can be multiplied by multiple times. So you don't have to remove a DPF to get high emissions. You can just have little cracks in the DPF, and it'll emit at many times the level of what it would normally emit if the DPF was functioning properly. So it's an important kind of concept in the inspection and maintenance industry to understand that vehicles often emit, even properly functioning vehicles will emit at varying levels. So you set up a kind of an arbitrary cut point between a normal emitter and an excessive emitter. So the normal emitters, even though their emissions vary quite a bit during the day, you segregate them and you say, okay, you passed. Maybe your emissions were a little higher than I expected, but you're okay. But you, on the other hand, you're emitting too much. There's something wrong. You need to go get your vehicle fixed. So that's the concept we need to keep in mind here. And up until the after-treatment system started to become prevalent in the diesel vehicle fleet, the old methods of identifying PM failures, passers was, I'll describe them, but again, none of them are really research-grade instruments. They're basically designed to find what an excessive emitter is versus a normal emitter. So the concept I want to talk again here about is adapting this kind of next generation PEMS to maybe dumb it down a little bit, simplify it, make it more specific to a given purpose, and perhaps be able to mass produce those and make them more like serving the inspection and maintenance market. So in the current ways of finding excessive emitters in the diesel area, there's 3 main ways. One is opacity, which some of the old timers here will remember back when, I think, 88, 89, ARB did a pilot study to figure out where that cut point would be for an opacity measurement. And they developed a test commonly called the snap acceleration test, where basically somebody sits and stomps on the pedal while the vehicle's stationary, and they're measuring the opacity of the plume coming out the exhaust pipe. And that was then modified into a formal protocol by SAE called J1667, called the snap acceleration test. That's what I'm going to call it here anyway. Another fairly prevalent around the world method is generically referred to as filter smoke number. And basically that's an atherometer where you pull a sample through a white filter paper and then you compare the reflectivity of the stain on the paper to the unstained paper. And that, the darker that is, the more PM, that kind of thing. So it's an analog to PM emissions. It's not a direct measurement of mass or anything. Kind of like opacity, it's an analog. Opacity works for coarse, visible type emissions, but nowadays that's not enough. And then there's the visual method where you stomp on the pedal or you go down the road, and if you can see a plume, then it fails. And again, that's not good enough nowadays anymore. So, quick description of PARSync for those who may not have been listening earlier. It's a next generation PEMS that has three ways of measuring particulate. One is opacity, one is laser light scattering, and the third is ionization. Excuse me. So as you can imagine, those three signals could be a little confusing because everyone's used to seeing one output. I'm measuring PM, I watch one curve, and as it goes up, that's more particulate. As it goes down, that's less. So watching three curves, that's hard to interpret. At least for me it is. So we thought, how about the concept of coming up with like an opacity or a filter smoke number analog for this? So we decided to call it PSN instead of FSN, PARSync number, and it basically combines the three outputs into a single number, and each of those outputs can be scaled using coefficients to help you tune PSN to be able to identify high emitters in a given country, or maybe it would be a worldwide type of thing, but you can scale them to find vehicles that exceed this hypothetical pass-fail, or not hypothetical, somewhat arbitrary pass-fail cut point. So we managed to identify someone who owned a vehicle with a DPF bypass. So it's a diesel truck with a valve that would allow them to send untreated exhaust past the DPF to simulate, like if the valve is closed, then all the exhaust goes through the DPF and it's very clean. If the valve is all the way open, almost all of the exhaust goes past the DPF and it's dirty, as if it didn't have a DPF. And this vehicle owner happened to know what settings constituted passing versus failing in their mind. And so we wanted to test our system, our concept, PSN, to see if we could identify what they called passing and failing. So what we did was we went to their location and set up our system on their vehicle, and we had a test protocol. Basically, it's a blind approach. We didn't know what settings they would be set to, but what we would do is they would adjust the DPF bypass, then we would tell them when we're ready for a measurement, and then they would do the snap acceleration, three pedal pushes, and then we'd say, okay, finished, then they would go to the next setting, but they wouldn't tell us what the settings were. So we did that 11 times, and here's the results. So each of these little numbers, I think you can read them pretty well. This is not a pointer. This is a pointer. Each of those represents the 11 tests, okay? So this is ambient air. Then we start sampling, and you can see this vehicle is very clean. So the first test, basically undetermined, you couldn't tell the difference between that and ambient air. The second test setting, that was obviously an elevated, there was a certain amount of bypass there. Fifth test, a lot of bypass, et cetera, et cetera, et cetera. So in the end, we sent them back the results, and we said, tests 1, 3, 4, 6, 8, 10, and 11 should be a pass, because either we can't tell the difference between that setting and ambient, or it's slightly elevated and just really there's not a obvious, issue. normal emitter. And then tests 2, 7, and 9 were a setting that could not be identified by opacity alone or visual inspection, but that the combined 3 signals did identify as a failure mode. And not only was it a failing mode, but each of those was the same mode. They were the same setting, we speculated, based on the area under the curve and the shape of the curve. Then number 5 was another setting that was extremely dirty, quote unquote, excessive, that even opacity would be able to identify. And we showed that actually in the 3 signal inputs after the fact. So in post-processing into one signal, we're able to differentiate between what this vehicle owner called passing and failing, normal emitting versus excessive emitting. And we were able to identify settings that opacity alone would not. So that's kind of the takeaway from here. What happens next? Well, we're going to find additional vehicle owners who have bypass valves. We already have one in mind. And begin looking at how maybe these 3 signals can be analyzed, like Carl already referred to look at failure modes and reasons for failures. Maybe we'll be able to find out things that help them repair their failure. And we are also starting to explore the possibility of a pilot program to kind of take this to the next level and look at setting a real cut point that applies, fleet-wide, kind of maybe based on standard levels, new vehicle standard levels. So, thank you very much for listening. We want to thank that folks who supported us anonymously and non-anonymously. And if you have any questions, these are the folks to direct them towards.